Okay. Hi, everybody. We continue our work regarding the interface between LabVIEW and Python by using Python node which exists in LabVIEW environment. We have discussed in the previous lecture few examples, and we are going to continue discussing more examples about this issue so that it will be covered completely and you can use it directly. Here we have an example where we use two functions in the same shell, in the same Python program. We want to add two variables x and y and return to the node the sum of both variables. And we also want to multiply them together and to return the result of multiplication to the Python node. As you see, this program here must be saved in a file in the documents or in the Python or anywhere convenient for you. It is already saved, and I have established the interface program in LabVIEW which realizes these requirements. So when we go to the LabVIEW, now I open LabVIEW 2025. I open the VI, which is here given a name or a number for one interface to Python functions in one program. So the program in Python is saved in Python folder with a name given fathi.python.py. This is the path to the file which is saved. If we look at the program, of course, it is not that difficult to understand. We have two functions there in Python. So here I have to create two nodes. Each node will realize one of the functions. Here, this node is dedicated to carry out the sum of x and y. Look, here is x fed to the first terminal here. Y to the second terminal. This terminal, as you see, is just to define the type of data of the output which we are expecting to have. The total of x and y is expected to be a numeric value. So here it is a numeric value of 0. And this here, I shall receive the returned value from Python. The same thing I do with the second node. I pass the variable here, as you see, and the second variable to the second input, and the output here will return the multiplication of both variables. Of course, I can here pass another two variables in addition to x and y. I can put here a variable here, so a constant with value equal to 7 or 8 or 15, any value, and another value here, and they will be multiplied, and these two values will be added. It depends what you want. For simplicity, I have just used the same input values x and y. But the first node, as you see, has the name of addition, which is there in Python. The second node has the name of the function, which is multiply, which is also fixed in Python. Because both of the files are given in one program there, so I have, and they exist in one file, which is this file. So as you see, we need here only a line to feed the path to this node and to feed the path to the other node at the same time. And that's it. Now, if we run the program, as you see, here we have an input 6, here an input 9. If we run the program, we shall find one of them adding 6 and 9, it gives 15. The other one, 6 multiplied by 9, will give 54. Of course, if you change it, let it be 7, for example, and this one, let it be, for example, 3. So 7 plus 3 will be 10, and the other value will be 21. So this is 10, and this is 21. So I have just wanted to show you that we have to assign a special node for each function existing in the Python program, which is going to be saved somewhere in the computer environment, and it will be called by each of the Python nodes. Okay, we finish with this example and move to another one. Why it is not moving for me? File exit, and that's it. Okay, let us move to another example. In this example, we shall make regression, linear regression, and I will illustrate to you how we can do that also by using Python interface node. This is the program with a function called run regression, which exists, as you see, in the Jupyter notebook in Python environment. So in order to implement this program, I import NumPy as NP, and from SKLEARN linear model, I import this function which realizes linear regression. We have created or defined the function run regression and passed there the variables which are going to be used. The first one is X, which represents the array which contains the features. The other one is the array which contains the target or targets if there are more than one. And the third variable here, new data, it is given this name, which represents really the data which is going to be used as a test portion. You remember, when working with linear regression, we usually train the model on some part of the available data, and another part of the available data is assigned to be used for testing only. It doesn't go through the fitting and learning process. So this new data represents a small portion of the data which is going to be used to test of course, the regressor, and to find the predicted related values. Okay, X here is expressed, as you see here, as an array, and it is reshaped because in linear regression, when we talk about the features, we have on one column for the rows, which defines the rows, and the other column, or more than column, which define the features. So if we have even at least one feature, we need to have two columns and a number of rows. So it is a two-dimensional. Usually it is a two-dimensional array, this one. You will see that when I supplied the X array in LabVIEW, it was there one-dimensional. And because the linear regression works with two-dimensional array, so I have to reshape the value here, the array, so that it will be two-dimensional array. And by this, the linear regression will work normally. Y is given as n pi array of Y. Here, we do not need to have two-dimensional because we have only one. I have suggested to have only one target. The dimension of the new data and the dimension of X must be the same because, as usual, you remember when we worked with SKLEARN, we take this data as 20% or 25% of the total data which we have, but it should have, then this means that it should have the same dimensions. So if X is a two or reshaped to be a two-dimensional, the new data will be the same. So it is an array which is reshaped to become two-dimensional. Now we initialize the regressor, linear regression function. It is called, and now it is assigned to an area. It is called a model here. We use this model to fit X and Y as usual. And by doing that, now the model has learned the data which we have, and it can give predictions, and it can give us also some information about the quality and some data which results at the end of regression, like the intercept value or the coefficients of regression. So now, having the model trained on the data set, we call the model and ask it to give us the value of the regression coefficients. Here, I am adding dot to list because we expect to have a number of coefficients here. Usually, the linear regressor gives the output as a list of values, and we assign this to a variable called coefficient. Model intercept also, so we get at the end a value which represents the intercept because we are talking about linear regression, so there should be some point as intercept point. Also, we can use the model to carry out prediction of the values which are within the new data. So here model, we call predict function and pass there the new data, which is as input for this function. and we ask to give it as also a list. So we will have now at the output a list which contains the predicted values. It is called predictions. Note that all these instructions are included within the run regression function. The run regression function ends with the word or the instruction return. Now it will return to the LabVIEW Python function the value of the coefficients, and the intercept value, and also a list of the predictions to the values which are given at the input, the new data. Let us go and see what happens there, what we will get there. So I go to LabVIEW. I open LabVIEW. And open the program of interest. Here it is number 5. Now, this program, as you see here, has a block diagram here. The program which I have discussed with you, which is in Python, in the Jupyter notebook, was saved in the computer, and it is given a name regression3.python, and it exists in the documents. Okay, so now the node here already knows the the path to the file where the program is saved. Also, I gave it the name, which is run regression, as exactly the same letters, capital or small, as it is in the Python program. We have expected to have at the output an intercept value, which is a numeric usually, and we also expect to have a list of coefficients, which is an array, and also we expect to have a list of values of the predicted values, which is an array. So at the input here, as you see, I have supplied with a cluster which includes the first expected output is the coefficients. This is as array, as you see here. And the second one expected is a numeric, which is called intercept. And the third value here, which is the predicted expected values. How to put them here is easy. Usually, suppose I want to have an array there, I go there to the array. I have a shell of the array. I put it here, and I put inside it an empty value of the type which I expect, and that's it. But it is not necessary for me, so we keep it as it is. Okay, so now we have, as you see, furnished a cluster with the types of data we are expecting to have at the output. This is the output, and this is the values which will be returned from the return statement in Python. This is the cluster at the output. This cluster now will be filled with the values. So as you see, it has a coefficient, one coefficient, because we have one line with one slope. It will have a one coefficient with number 2. The slope is 2. The intercept has a value of 0. This means that the line begins at the beginning of the coordinates. And we have predicted two values with 12 and 14 values against the input values, which I have supposed 6 and 7. This is the test values which I suggested. These are the predicted values. If I change this value, for example, to number 8, and this value, for example, to number 23, so if I run the program, I shall get here another two corresponding values for them. Okay, now these are the values which are predicted by our linear regressor for these two values. Having these two objects, you can judge that the system has an errors at the output, at the input, or at the output. When you see this green text, this means that the program is already functioning right, and there is no problem. If you will find a red cross here, so this means that there is some problem, and the problem will be given to you here to take care of it. Now, when we go to the input, as you see, as an input here, I have given the system this array, which is, as you see, one-dimensional array. In LabVIEW, it is one-dimensional array. And the target is also given as one-dimensional array. And because this is one-dimensional array, so X new data should be also one-dimensional array. They are of the same, as you see, let me say the same type, two-dimensional. Now, if I go to the block diagram and have a look, so X in here is the terminal, which represents the input array. And as you see, it is really, with one line, it is a one-dimensional array. And this is Y, and it is also given as one-dimensional array, as you see here. And the third one, which is the test values, is given a one-dimensional array because I have given Xn as one-dimensional array. With this, the program cannot work well, except if you go to the original program there and be sure that it adds or it converts the one-dimensional array to a two-dimensional array. So X, which is at the input now, it is reshaped, and now it became a two-dimensional. This means that the run regression function is okay, and the linear regressor will work on it properly. When you pass here X, it will consider it as two-dimensional and no problem. Y, it is kept as it is, but new data, which is the test data, it is reshaped as we reshaped X. So when we work here with it again, when we make a prediction and pass it here, the model will work on it and faces no problems. Okay, now let us go again to the block diagram and see. This is the output. You can look at the returned values here, as you see, and maybe more convenient to you to unbundle the cluster at the output here and rewrite unbundle by name I have taken so that to see every element. And now this cluster will give you the coefficient and the intercept value and the array of predicted values. So we have two values only here. If you double click, you can see them, 1646. The coefficient doesn't change, and as you see, everything is normal. So I think now maybe we have given the Python node a real practical duty to work as part of a regression task. Let us also consider other issues related to the dimensions of the X array and the Y array. Let us go and look at another option here, which is the example number 5.1. In 5.1, as you see here, the input X is given as a two-dimensional. Why it is one-dimensional? Because only we have one target. As this one is two-dimensional, so the test data will be two-dimensional. Columns and features. If we go to the Python program and look what is there, we shall see that this array now is not reshaped there. I didn't reshape it because it is already two-dimensional and it doesn't need to be reshaped. Neither this one also, it doesn't require to be reshaped. So if we go and have a look at it, here it is. The name is the same, run regression. The input variables X and Y and new data is the same as before. X NP array of X, but I didn't reshape it. I didn't increase the dimension here. It is already two-dimensional, so it's okay. Y, it is the same thing. It is still one-dimensional, but the new data also is not reshaped as we did before. If you remember here, we did reshape the new data, which is the testing data, and we reshaped the X to have two-dimensional so that linear regression will work with it. Now, I didn't do that. It is not required to do that because this is done by LabVIEW at the same input. And now if we run this program there, it will work well and it will give correct answers without any problems. If you go back here, we have given, of course, the values which are given here may be different than those which I have before. Now, but if I run it, before running, I can check the program. It is okay here. It is normal. This is the expected output, the coefficients and the intercept and the prediction values for these values. Now, if I run the program, it is running okay. Now you see the coefficient has a new value, the intercept has a new value, and the predicted values for these values 6 and 7 now they are 7 and 8.5. Also, as I did in the previous lecture, I have taken out the value of the coefficient. Here it is alone shown. The intercept is also alone shown, and the predicted values are given as an array external value. They are exactly the same. I have also tried to show you how we can plot this in LabVIEW. This is the linear fit. This is the line which fits the data set. Look at the intercept. It must be equal to about 3. Here 0. Here 3. It is about 3. A little bit less. Here it is a little bit less. This is the intercept value. And coefficient is, of course, the slope of this line. The slope means the tangents. If you take away this value from here to here, 3, for example, 3, and here it is about, let me say, 5.5. 5.5 divided by 3, it gives you the slope. Let me see, 5, and it is about 5.4. 5.4. 5.4 divided by 3 gives me 1.8. 8.1. 1.8. Why? This depends on the coordinates. They are inversed here. Okay, no problem. So if we divide 3 by 5.5, 3 divide 5.5, it will give you, no, maybe it is not correct. But here it is all, I'm sure here it is correct. Let me see. Number like this one here, it is very close, 6, for example, by 4, 1.5. The slope here is 0.8. If you divide from here to here, 5 by 7, the slope is the tangents of this angle. It should be equal to the value from here. It begins from 3 to 5. It begins from 0 to 5. It means 5 here. But up at 1, 2, 3, 4. 4 by divided by 4 gives 8.1. Okay, normal. It is normal. So as you see, these dots, white dots, represent the original value. So if I go back to the program and look at the block diagram, how I did it. So this is, of course, a bundle element, and this is another bundle element. Here I have take X, Y, and X. This is the original values, X and Y. And here I take again X and the predicted value. Now I have at the output a cluster and another cluster. I made an array of them. And this array is displayed here, as you see, as a line. To be sure, you can run it again. Now it is running, as you see it is red. It gives exactly the same results. So what I have in mind, I wanted to show you that you must keep eye on the dimension of the array, which represents the feature table and the target table and the testing value table. And if necessary, you can modify from one-dimensional to two-dimensional, or from two-dimensional to one-dimensional. You can do this either in LabVIEW, or you can do it within the program in Python. Okay, let us go and see another example here about this issue. don't see. Let us go and see, open 5.2. In 5.2, here at the input we have two-dimensional normal, and it is, yes, 5.2, and here it is exactly the same as I did. What is there here again? Here is the two-dimensional input, and here is the one-dimensional Y, and here is the testing input two-dimensional. No problem. It should work okay and without any problems. Let me go back and see what we have before. I have forgotten the difference between them, if there is a difference. Okay, let's go out. Or from here, we can open it again. Open 5.1. We were here. Now, there is a difference, of course. Here, as you see, the input features array is two-dimensional. And if you go to the block diagram, it is here two-dimensional. But what I have done, I have changed it, reshaped it to one-dimensional. The same thing is applied to the testing portion. It is two-dimensional, but I have reshaped it to one-dimensional, which means that in Python, I have to take care there of it and reshape it. This must be reshaped in Python. But if I used it directly, two-dimensional, and this one two-dimensional, there it is not required. So let us go back and see. Here, as you see, we did not use any reshaping because it is already in LabVIEW reshaped. This is for 5.2. Here, we have reshaped it again with 5.1. Why? Because there in LabVIEW, I have reshaped it to one-dimensional, and this one was also reshaped, so I need to reshape it back to two-dimensional in Python. This is the idea which I wanted to illustrate with you so that you will not fall in these faults. Okay, let us go to another program also to work with you. These are not necessary now. I have illustrated the three different possibilities. And now I shall go and illustrate with you another program, number 6, linear regression with SKLEARN. This is different because, as you see in SKLEARN, you remember, we usually divide the data to two parts. One part is for training of the model, and the other part which is assigned for testing. And the testing, usually, as I have mentioned just now, is about 20% from the whole data set. Here, we shall work with a program which illustrates how to interface such a program which is written in Python with the appropriate program in LabVIEW. Let me go and show you, give you an idea about the original program which is in Python. This is the program. At the end, I shall have the distribution or the scatter plot of the data set, and this is the linear fit done by linear regression function. So as a beginning, we have imported matplotlib as a library required for plotting. We have also from the linear model imported linear regression because we are going to work with this function. And from the model selection, which is in SKLEARN, we also imported a train test split function. Here, this function, which I told you, which splits the dataset to 4 parts. 2 of them are X train and X test, and the other 2 Y train and Y test. And also I have imported from the SKLEARN matrices 2 metrics to be used to give an idea about the degree of accuracy of the work. The first one mean squared error and the other one R squared score. They will be used also in order to guess about the accuracy of the work. Okay, so at first we have used a seed 42 because we are working with random functions and we need the random function to give the same result for every run of the program. So I am accustomed to put 42 to guarantee reproducibility of the generated random values. Now I am using the NumPy rand, and I have to generate for 500 points, 500 samples, 500 rows, and 1 feature. 2 multiplied by the values which are randomly selected here, which result in an array with a number of rows equal 500 and a value which represents the feature here multiplied by 2. Okay, this is X. Y is also a linear combination with X. X is now included in Y. Y depends on X. It is a dependent variable. This is independent variable. This is a dependent variable or the target. And as you see, it is reshaped also so that it copes with X. Now, what I have done, I have taken the X input, gave it a name x.csv, comma, separated values, separated by a comma, and this array of X now is saved by using NumPy save txt as a CSV file in the computer. So I have just saved it as a CSV file. Why? The idea here, I want to use the same values which are used in Python for X and for Y in LabVIEW. LabVIEW can read the CSV file, which is saved in the computer by using NumPy save txt. So, shortly speaking, I am saving the value of X which is generated here in a file in the computer, and this file will be read by LabVIEW, and these values of X will be taken as input to the node. The same thing here I did with Y. I call it y.csv. This is the original Y. This is the new name, y.csv, with comma separated values. And it is also saved in the computer. Where it is saved, it is not difficult to know. We can go to the program here. Go to the front panel. Here, one of them. This is the Y. So the X should be above. It is saved in Python. And its name, as I gave it there, x.csv. The other one is also saved in Python and has a name called y.csv. You want to see it? No problem, we can see it. Here we can go to the Python. Now I am in Python, as you see, and xcsv and ycsv. They should be here. XY at the end, usually. This is the xcsv file, and there should be downwards the Y. This is the ycsv file. So just I wanted to show you that they are already saved. Now we are back here. So this X array and Y array are saved as CSV files, and you have seen that. Here, just to show you, I have shown the shape of X, the shape of Y, and a sample of 5 readings of X and Y. Here they are. The shape of X 500 samples with one feature. The shape of Y 500 with one, it is reshaped, as you see there. And I have read some values. When you write X head, the first 5 readings, 1, 2, 3, 4, 5. These are the first 5 values of X and the first 5 values of the Y. And also I have taken 1, 2, 3, 4, 5, 6, 7, the first 7 readings of the X text. Now, which we X test, which is going to appear when we use the SKLEARN train test split function. Now it's term here. So train test split function between brackets, we pass there the values of X and the Y, and we inform the function that we want the test portion to be 20%, and the selection will be with a random state equal 42. So at the output now we shall have 4 arrays, X train, Y train. These are the values which is going to be used to train the model. And this is X test, which is going to be used to make predictions on the model. And Y test may be used if we want to make plotting of the curves. Okay, so now we have divided the data set to training and test portions. I have printed also some of them here and some of them here, but I have again also saved X test as CSV file, X test it is saved as X test CSV file and Y test also as CSV file. Okay, now we initiate our regressor, linear regression function, and at the end we have an object model which is going to be used to fit this model with the data set. So model dot fit a data set which we have here, X train and Y train, already known to us. Now, at the end of this operation, the model has learned the data set and is able to carry out predictions and give us also some information about the process. To make predictions, we use the model dot predict, and we pass there X test, which is about 20% of the values. And I have also printed the predicted values, the first 5 values, just to show you what is their level. Y predicted here, 1, 2, 3, 4. These are the predicted first 5 values for the first values of the X test. For this value, we have this corresponding value. For the other value here, we have another value, and so on. So for each value of the X test, we have a corresponding value of the Y. Here, Y test and Y predict. Y test, Y predict. So we have got the value of Y predict from X text. And now, if we want to compare between the test Y and the predicted Y, we can use mean squared error function, which has been already imported. Here it is imported, or we can use R squared score, or we can use both. We have already talked about them. We used them previously. So we used the first mean squared error and passed Y test, Y predict, and also used R squared score and passed the same values Y test and Y predict to have an idea about the values of the mean square error and the R squared. And I have printed them also. The last thing which we have done here, we want to plot the linear regression line on the data set. So we have created a figure object with this given size. We plotted a scatter plot of the X test, Y test, and we plot a line with of the X test with the Y predict. These are shown here. The blue points represent the X test with the Y test, and the red one represents the X test and the Y predicted values. As you see, 2 notes interesting here. One of them is, remember that linear regression is usually and perfectly works when the original data set has an orientation as a line. Look how the points are distributed, and they give an idea that they are a line-wise located, not a parabola or not a sine wave. It is more nearer to real linear distribution. And this line, which has only one slope, as you see, and has an intercept value here. If you go down, here is the 0. So this is the intercept. It is about here 10, about 6 or 7. Now we shall see. So the model intercept 7.45. The slope is 13.23. The mean square error 4.18. And the R squared value is 0.93, which is high comparatively and very good. What I have explained now is, as usual, a usual traditional work which we have done before when we used linear regressors. So here we did not include any function. We did not modify this program to be interfaced with LabVIEW. To do that, I should have done worse the same program, but a little bit modified so that it could be used with LabVIEW. So first of all, I am not going to use in LabVIEW matplotlib pyplot. It is not required there, so I have taken it out by this hash sign here, and I keep the other required functions and libraries. I have created a function, define LG, LG as shortened name for linear regression, a name of the function, and this function will have the values of x, y, and x10. So these are the variables which must be fed from LabVIEW, from the node. This x now will be fed by the values which I have saved previously. When I run that program, you remember, the values of x now are there saved, the values of y are there saved, and the values of x text are there saved. So if I feed them to the node, I expect to have exactly the same answer. Now, as I did within the program, as I did before, I have splitted the data set to training and testing parts. I have called the regressor and initialized it. Now I have the model. This all done within the program. I have fitted the regressor with X train and Y train as I did before. And the values now already known because I know X train and X test and Y train from X and Y, and X and Y are known to me here. They are fit to the program. So everything is available. At the end, I predict for the given text values, what are the predicted values? Okay. And at last, I have evaluated the performance of the system by using here by using R2, by using square score. I didn't use the mean square error. Why? Maybe it is not necessary, just like that. Or maybe I have furnished the cluster at the input of the Python node with only one matrix, which is R squared. Anyhow, here the program is about to finish because I am now giving return. I am asking the program here to return to LabVIEW to the node the value of the coefficient and the value of the intercept and the values of the predicted values. Now let us go back and see how we do that in LabVIEW. So here is the Python node. This is the close session. This is the open session. I am working with the function LG. It is the name. The program which I have just explained to you is saved in the computer as kamal.py. So this is the name, and it is saved in the documents. Okay. Now, I have an idea about the values which I am going to read. So I have included here an array, which means that I shall receive an array of values representing the coefficients if they are more than one. The intercept value, this is only one numeric. The predictions as an array, and R square. So I am expecting to have these types, 4 types of data: array, numeric value, array, numeric value. If you go to the block diagram, you can see that the output should include these values. This is the output. If I double click it, here is the output, the cluster at the output. It includes the coefficient. This is the coefficient value. This is the intercept value. These are the predictions with the same sequence, the predictions for the values which I have. I can resize it, I can like this, and this is the score or the R squared score. Again, if this is not adequate for you, you can split or you can unbundle it as I did in the block diagram here. I take this cluster and unbundle it by name, and I will get the coefficients here, the intercept, predictions, and the R squared. All these values now are, here they are given outside. So this R squared is the same value as here. The predictions, here they are beginning with 2447 and continues to the end. This is the intercept value, exactly the same value as here. The coefficient value, exactly the same word as there. Now, this is the function in LabVIEW which reads the file of X which I have saved. The path to that file is here. If you look, you find it in CS. I have shown you, it is in Python with the name X CSV, and the same thing with Y CSV. Anyhow, to show you how it works, if you go to the block diagram here, you will see this file here, this delimited, read delimited spreadsheet VI. This is this function. It gives you at the output a double order or shape, second order array. Here it is. The values, sorry, now you will see it. Here are the values. 74908. These are the values, the first value, the second value, the third value. These are the values obtained. These are here the values obtained from this function which reads this file. If you go back to our function, you will see that this is the value exactly 0.749, exactly the same value, 1.9. The same values which were in Python are now given to LabVIEW. Again, you look at it, here it is, here the other one, and so on, and so on. So here now I have read the data which is saved in the file as a 2-dimensional array, and this is which is required. So I take it directly and feed it to the node. To be sure about the values, I have taken the size of it. It is 500 samples with one feature, normal. as it should be, exactly as required. Now I have again read the y as two-dimensional, but because I need the y, because I have one shape, I need only one dimensional. So I have here reshaped, the array in LabVIEW because it has 500 points. So now I put this input 500 and I get now on the output a flattened array with one dimension which fits the node. The third value here should be the value which represents the test value. Here they are saved. This function reads them. I have reshaped them to one-dimensional and fed them to the third input. Now we have a complete picture about all what we have. What is left? In order to draw, I can also draw in LabVIEW as I draw in Python. Here is the plot which represents the xy with the predicted xy. Here is the plot which represents the values x train and y train, the original values in white, and the predicted line values in red, exactly as you have seen with Python. Concerning the values which we are interested with, which is the coefficient and the intercept and the R-square and the predicted values, they are exactly the same as we have read within Python. You can be sure, you can read this lecture once and more, and you will be sure that it gives you exactly the same answer. Anyhow, according to me, it seems to me that working with the Python node is not that difficult. It is not a mystery. It is really practicable. All what do you need is to work with it one or two examples to train yourself and to take care of the dimensions of the arrays which you work with. And that's it. And I hope that you can do this more and more on your own. Really, I have prepared for you another two examples, example number 7 and example number 7.2, as I think. I have no time today to discuss it with you. I shall see if it is better to discuss it with you in the next lecture or to leave it and to discuss with you the interfacing between Python and LabVIEW through the discussion of the Reg and Lazo regression algorithms, because I want to tell you about them something and to introduce you to these two algorithms and how they are realized in Python and also how they are realized in LabVIEW. Well, I prefer this option really. So anyhow, I am thinking to do that in the coming lecture. For now, it is sufficient. I hope that you have understood everything and that everything is clear. I didn't leave any point without explanation. Wishing you a happy day and see you.